Okay, going to start. Okay, magnetic field. Uh, we start with the chapter number 16 is magnetic field. And then we have 1, 2, 3, 4, 5, 6, 7, 7 subtopic of it. Let's try to finish up to summarize it up. Okay, magnetic field, as a moving charge. Actually, it's a magnetic field. Yep. Experience a magnetic force when a moving charge particle must be moving charge particle that experience a magnetic force. Magnetic field produced by there are so many sources of magnetic field. One is current carrying conductor, a permanent magnet of the earth, and the direction is from the north pole pointing towards the south pole. So if you have a north, it's go to the south. The magnetic field line from the north goes to the south. And if you remind yourself, you have to remind yourself the earth, the south pole is on the top. The south pole is on the top. The north pole is at the bottom. But when you use a compass, the north will be attracted to the south, and the south will be attracted to the north. Right. So you see that the north of the compass is showing the south. North compass showing the south uh of the earth. So actually the south at the top, north at the bottom. Okay. And for like the magnetic field, there's so many sources. So due current in solenoid, 1 is permanent magnet. Number 2, magnetic field of the earth. Number 3, and due to the strong straight line current. So it's 3 or 4 of them will produce a magnetic field. So force a moving charge. Now we have a moving charge. Charge is moving. I put a Q. Q is moving. If the Q is moving, it will be produced a magnetic field. It must be moving. If it's static, no magnetic field will be produced. Okay. So what are the factors of the magnetic field? One is uh, magnitude of the charge. How big is the charge? Number 2 factors will be the magnitude of the density marked by this magnetic flux density B, and depends on the velocity of the moving charge. So these are the factors who determine how big, how strong is the magnetic field. So if we conclude that F, the force of the magnetic field, is determined by Q V B sine theta. Okay. So if the positive charge Q and you have to use your left hand rule, FBI force at the top. So this one we can label them as F. This is B and this is I. Force pointing up. Index finger pointing to the magnetic field, and current where the Q or the charge is moving, we label it as SI or FBI. Okay. So magnetic flux density at one point magnetic field is defined as magnetic force acting on a unit charge perpendicularly with magnetic field with unit velocity is given by equation V equals to F over QVB sin theta. Actually came from on top over here. Okay, F equals to QVB sin theta. So B is actually how big, how strong, or how weak is the magnetic field is determined by how much the force by the magnetic field and divided by Q will be sin theta. So F magnetic force, Q is charge of the particle, V is the velocity, and angle is between the magnetic field and direction of the motion. For example, over here we have a proton Q travels with the speed of 3.0 times 6 power 6 as angle of 337 with the angle of magnetic field. Okay, so that's from the top view, it was like it's 37 degrees. So this is magnetic field. This will be the velocity of the Q. Okay, so 37 degrees. So the magnetic field B is 0.30 Tesla. So calculate the magnitude magnetic force of the proton and the proton acceleration. So from F equal to Q V B sin theta. Okay, F equal QV sin theta, you put in the charge of the proton, and then you put in the velocity, substitute the velocity of the proton, the moving proton, and how much is the how strong is the magnetic field, sin theta, and then you have there 8.7 times 10 power negative 14 Newton. The second question is, it's asking about how much is the proton acceleration. The proton acceleration is, you can get from A equals to F over M. F is the how much the force of the magnetic field divide the mass of the proton. So it is 5.2 times 5.2 times 10 power 12 meter per second squared. Okay. Motion of charged particle in uniform magnetic field B. One is parallel to magnetic field. When the moving charge is parallel to magnetic field, there is no magnetic force acting particle, and there's no acceleration. Particle continues to travel with a constant velocity. So there are no, if it was B and V like that, okay, V and B in the same direction, there will be no deflection, okay, because there are no zero, there will be zero magnetic field forces acting on the charge. If perpendicular to the magnetic field, if the charge particle moving perpendicular to magnetic field, so FBQ sum beta, so FBQV. Now, since force is always perpendicular to direction of the motion, therefore the force is used to change the direction of motion but not increase the speed of the particle. The force is used as centripetal force, therefore the particle moves to circular path and show diagram above. So, if we release, say let's say this is a B, B is pointing. Remember, this is pointing inward. This is pointing outward. So B pointing down. Use your left hand rule. B pointing towards the screen, and current is the V pointing up. So F, your thumb is pushing, pointing towards the center of the motion. So F is pointing here. Actually, let's say the Q is from here. It goes to the region where we have a magnetic field. When it enters magnetic field, it will not be in straight line anymore. It will be a curve, and then at the end of the curve will be going through a circular motion like this and forever like this. Okay. Actually, if we if you see the actual experiment, it will be a spiral going in into that. But actually, if for our syllabus, we just assume that it will be a circular motion like this, okay, and forever like that. Okay. So FQV, this is magnetic field forced by acceleration, FC, centripetal force equals to FV. So R radius is mv over QV. The period of and the frequency of the motion given by T equals to T equals to 2 pi R over V, and F equals to QV over 2m. Okay. So let's say for proton move perpendicular to uniform field B at, this is the velocity, explain acceleration at this A, between magnetic flux density. So we using B equals to F over QV. Okay, because sin theta is perpendicular, no more sin theta. So F equals to MA divided by QV, there you have 0.21 Tesla. Okay, second question. Calculate the radius of the circular path. So circular path, we can use as Q equals R equals to MV over QB. Or we can use also F equal MA. So you have V square. So V square over A, then you have 0.5 meter is the radius of the circular motion. Okay, so this is the diagram. Now we have a force on the current carrying conductor. Okay, force on the current carrying conductor. if we have a conductor, there will be a current. There is not a single, but many Q. There are many Q. There is a running through the conductor. So there'll be NAL, number of charge in the wire will be NAL. It depends on how long is the conductor and how much is the cross sectional of the wire and how much is the number of particle density. So everything has to be counted because it's a no more one single charge. So there we have F equals QV sin theta. So but I equals to Navi. Okay. The velocity of wire is I equals to Navi. I equals to NAVE Navi. So F equals to BI sin theta. So F T. Okay. F equals to BIL sin theta. So how long is the conductor? We have to take into account how it will be determine the factor how big is the magnetic field. Okay. If the B field is some arbitrary direction of with respect to the length of the wire, so FBRL sin theta, where the angle is between B vector and I vector. Okay, so this is the B. Let's say the B and I has a little bit slight of different angle, so you have to put BIL sin theta. For example, this one, straight long wire is 2 meter. Current flow through the conductor is 1.5 ampere. The conductor is placed to uniform magnetic field B. The magnitude is 3.0 times 10 power negative 3 Tesla. The angle between flux and the conductor is 30 degrees. Calculate the force. So F equals to BIL sin theta. So this is B. This is L 1.5. So sin theta will be 2 sin theta. Okay. Why we have 2? Is it correct? Yeah, 2 sin theta. I don't think, maybe it's a typo there. Okay. Sin theta 30 degrees. So there you have 4.5 Newton. Okay, Newton down there. So direction of force is given by, you use your left hand rule. Force pointing up, B pointing toward the screen, I pointing to the left, F force is pointing up. So actually there will be force that lifting this current, this conductor going up. Magnetic field to the current. Ampere law, this is very important. Okay, because in your MAS, okay, you will be determined. You have to define what is Ampere law. If you check back, you have to state the Ampere law over here and use it to derive B equals to U naught I 2 pi R. So this is derivation plus the state. So actually, if they giving you question, they will ask you to state and derive one in the one question usually, in essay. So where is it? Okay. So Ampere law, it says that for that any closed loop, the sum of length element times the magnetic field in the direction of a length element is equal to product of permeability of vacuum U naught and the current enclosed by the path. Okay. So it says that there is one single current carrying conductor over here. So this I and the surrounding of it with the R, okay, so there will be ds over here. So this is s, you can see that ds. So this is every s over here, okay, small s integral, okay, you're not. So you say that the integral of b ds is equal to u naught I. This is what you say, enclose, enclose. Okay. So B, how much is the B? I mean, the magnetic field produced by this current carrying conductor, times with the small s over here. Sometimes they use L, sometimes they use L. Sometimes you use S, sometimes they use L. But it's actually the same meaning. L and S equals to U naught I U naught I enclosed. Okay. Remember, U naught, when you're dealing with B, you are using U naught. If you're dealing with E, you are using epsilon naught. Okay. Both of them are not same. Both of them are different constant number. Okay. So B times IL U naught I. So from there, okay, from there, this is for one single wire. This is a situation for three wires current conductor, but they have, you can count it by using the same closed loop over here. This is a closed loop DL. Okay. So application of reward to derive expression B into long straight conducting wire. So over here, so let's say we use the Ampere law to derive. So B times dl, B cos theta dl equals to B cos theta 0 times 2 pi r. Why 2 pi r? Because it's the perimeter of the circle. It's 2 pi r is the perimeter of the circle, right? So that's why you have 2 pi r. So cos theta is 1, so 2 pi r b. So everything over here is equals to pi u naught I. So 2 pi r b equals to u naught I. So b equals to u naught I divided by 2 pi r. Now you have the derivation of the long wide current kinetic conductor. Okay. A magnetic circular coil. So we have a magnetic circle over here. So it's given by u naught r and I over 2 pi r. This one does not to be derived. No need derivation. If we check at the minimum executable, he said to use the formula for circular coil Bu naught and I, and use the circular coil for solenoid. So this one no need derivation. No derivation. Only this part is a derivation. So don't try to derive it. Okay, it will take all your neurons. Okay, save your hard disk. Okay, this is not derivation. So you just remember B equals to U naught and I divided by pi r for magnetic single coil. Okay, next. For long solenoid, okay, we use B equals to U naught and I. Also no derivation. Just memorize it. Okay. So example 1, we skip this one. For long straight wire, B equals to U naught I to pi r. There you have for center of solenoid. There will be U naught U and I over L, that is 5.3 times power 2. If we have a solenoid, actually over here, this is solenoid, we only can count the magnetic field at this center of it only, over this side. Because at this side, okay, at this center, the magnetic field are constant over here. Actually, it's easier to find, okay, because they are much more easier concentrated. But at this point, let's say you want to find at this point or this point or this point, is harder because the concentration is not there. The lines are not concentrated at that point. So that's why we say the center of solenoid is actually at this point only. Okay, not the other side. Force between two carrying conductors. Okay, force between two carrying conductors. Okay, so using B equals to U naught I over 2 pi A. A stands for how much the distance between left carrying conductor and the right side. Okay, so force on the wire will be U naught I, I1, I2 over 2 pi A. Okay. Let's say you need to derive. Yes, you have to derive F equals to E naught for both current carrying conductor. And okay, so both of them are affected actually. So this one you have to derive. Okay, you know I1, I2 over 2 pi L. Okay. Okay, for example, we take this example. We try this example. Two wires of 2.0 meter long, apply the cord are 3 mA apart and carry current of 8 ampere DC. Of course, I forgot to tell you, it must be DC. The current carrying conductor must be in DC. Calculate the force one wire exert on the other. So F, you know I1, I2 over 2 pi times L. Okay. So it says that 2 meter around, long, and then 3 mm apart. The current with 8A, both of them, and this is the U naught. And then 2 pi r is a constant. Then you have 8.5 times 10 power negative 3 Newton. Okay, so there will 8.5. Okay, now we you should know that if the current, let's say, explain not in this. Oh no, if the current has same, both of them has same direction, the current moving in same direction, is it going to be attraction or repulsion? Okay, Shika, Usha?
Repulsion. Repulsion also.
Hmm?
Repulsion.
Repulsion.
Yeah.
Okay. So let's check back with our theory. So this is first conductor. The first conductor, and this is the second conductor over here. Okay. So first conductor, we have a magnetic field. We produce magnetic field. We assume it going towards the screen. So I put towards the screen. So current going in. This one also current going in. So the first current conductor pointing in. So if you use right hand rule, the right hand grip, it shows that the point it will be B over here. Okay. You produce B on the second cable going down. So you use the right hand rule, B pointing down, B pointing downwards, current pointing towards into the left hand rule, B pointing down, middle finger goes into the screen, and force will be pointing this way. Okay. For the second current conductor, it will produce, use the right hand rule, it produce magnetic field in this direction B, right? Going up. So left hand rule, B pointing up and pointing down. So F is pointing towards the center. So F is pointing this way. So if both of them had the same direction of current, both of them are having attraction. Okay, if one is going up, one is going down, there will be a repulsion. So the one we are counting just now, this is the force of, if both of them are same direction, this is force of attraction. how much the force of attraction between the two current carrying wires. Okay. Determine the ratio of EM by Thomson experiment. So if we have we combine electric force and magnetic force, okay. So we can use conservation of energy. Kinetic energy gained by electron is work done by electrostatic potential. So half mv square equals to ev. Okay. You should know how to convert ev into joule and joule into ev and how to process it. Right. So v equals to, okay, bigger. Okay. So half mv square equals to ev, and v, the velocity of the particles, okay, will be equals to 2 ev divided by me. So electric force Fe equals to magnetic force when it's equilibrium. It means that it passes through without any deflection. Bev equals to E. E over here is the charge. This is the electric field. Okay. And BeV, I think this one can be cancelled, right? Okay, so V, okay, V equals to E over B. So from equation 1 and 2, we can compute that E over M, okay, equals to E square over 2VB. But this is very important. It says that when the particles does not deflect, goes down straight with the some velocity, it means with the certain velocity, it means that E over B is E with the ratio of it. Then we have the how much is the speed of the particles. Determine any positive charge QM using a Q mass spectrometer. This one I think is in your chemistry sem 1. Okay, they already introduced you with this apparatus, mass spectrometer, where particles are isolated in anode, goes to cathode, and then by the mass, by the difference on mass, some will be deflected with lower R, some will be deflected with higher R. It depends on how big is the mass of the particle. Okay. So this one I think you can read by yourself. Given you this slides already. Okay. Hall effect. Okay, Hall effect is when the particles, it was like this. Okay. Oh, Hall effect. When the particles, let's say this is conductor. Okay. And then this is positive charge and negative charge. When the current flows, positive and negative charge, and then at the same time you put in this conductor in the region of a magnetic field. Let's say magnetic field is pointing towards inside the screen. Okay, there will be a deflection. Okay, the charge will be FE inside. I current goes here. Got it. Wait, pointing there. This one pointing down. Okay, so the positive charge will be pointing downwards. Positive charge will be pointing downwards and stuck at the bottom. Okay, and the negative charge will be pointing upwards in this side. So what happened is the positive charge, no, what happened is that the positive charge will be stuck at the bottom, okay, because the magnetic field pushing them down, and negative on the top. Okay, sorry, this is negative. the negative charge will be stuck at the top. And because we have a potential difference between these two regions, they made their own. When they what happened? Okay, before that happened potential difference. After they have fill up everything on top and bottom, the next charge, I mean the positive and negative, can be flow directly straight because there are no more places for them. They can go straight. Okay, and after that, there will be potential difference between top and the bottom. So there will be E over here. Electric field coming from E, from the positive to negative. And if you take the voltmeter, there will be a reading of a voltage over here because the positive going to negative. There will be E, potential difference between E, bottom plate and the top plate of the conductor. It's not a plate, actually it's a conductor. Top, bottom and the top. So and when it has happen, you have Fe equals to Fm, okay, and Ev equals Bev, and you have E equals to V over D and Vh. This is Hall voltage BVD. So it means that the voltage on top and the bottom, Vh, is the how much the potential difference between top to bottom. Okay. But the current is related battery by I equals Navi, then VH also we can use BID divided by NTDE, or we can use VH equals to BI over NET. Okay. So Hall voltage is affected by how much of course it's affected by how much the magnetic field, how big or strong is the magnetic field, and how strong is the current divided by NET. Okay. Uh the T here, sometimes obviously you can see that the T here, you have to make sure you never being confused. Okay, because the T, you see the T is actually, oh, it didn't show over here. The T is actually the distance between these two. You see this one? Okay, it's a distance between this point and this point. Front and at the back. Okay, front and the back. It's not distance between up and down. Okay, so students tend to make mistake on the T. Where is the T? Okay, so the T is front to the back. Okay, okay. So Hall effect in semiconductor P, there you have majority charge carriers are completed with charge hole drift out to side. So there you have a Hall effect semiconductor. Okay, so this one, for this example, are all the conclusion of the what I have discussed just now. Okay, Abi, you have this PowerPoint, right? You have this PDF, right?
Yes, sir.
Okay, so you can read this one by yourself slowly. Okay, and then if you don't have any, if you have difficulties of answering it, you can ask me. So I think this is not very hard for you to do. Right. Okay. Any question?
No, sir.
No. All right. So, uh, so for conclusion, this chapter there are derivation. Let's see the derivation. Derive f equals to ILB sine theta. This is first derivation. Second derivation is b equals to u naught I over 2 pi r. This is derivation number 2. Also, you have to write f equals to u naught I1 I2 L over 2 pi d. And that's it. Okay, there are 3 derivations. You have to take care of it. Okay. So I think that's for all. Induction Next time, Abi, I don't have much of time. Can next time,
Okay,
Darshan.
sir.
Okay.
Okay, sir.
Okay. So see you tomorrow in the class.